Hi, everybody. Chapter 2. Like I said, I just want to have this up in case we're not there, or in case all of life, happens. So what are we talking about in Chapter 2? It's going to be control of the internal environment. I'm really hoping that wind is not too loud or too irritating. So our internal environment is going to be us. What's our normal? What's our homeostasis look like? How do we maintain what we're doing? Homeostasis is defined as that constant normal internal environment. We're not always normal. We're not always at rest. And that's what homeostasis is kind of referring to. So dynamically, when we're doing things, when we're engaged in exercise and activity, we have to get to a normal. And that normal is just defined as unchanging. So we kind of hit that steady state. It's not what we are at rest, but it's an equal give and take. So we look at having been able to achieve that balance between what demands we have and our response to those demands. Now, two of the ways we can modify this is going to be temperature and arterial blood pressure. When we start to exercise, we are in fact going to see a change in that core body temperature. So if we look at things, at rest to exercise, our temperature is going to increase until we hit kind of a steady state, a plateau, where we just maintain a normal. And once we've maintained that normal, then we can continue basically unchanging in the activity. So as long as we have energy to do our demands, temperature isn't going to be what shuts us down. Arterial blood pressure, when we look at that, it's a pump. So though it oscillates over time, that mean pressure remains the same. We don't see huge highs and lows. So remembering, homeostasis is the maintenance of constant internal environment during resting conditions. Steady state is also going to be that constant internal environment, but it isn't necessarily what it would be at rest. How do we control it? We can control it at the cellular level, or we can control it based on systems. So from an intracellular control system level, the protein breakdown and synthesis, energy production, how we maintain our stored nutrients, all of those things will give us control over the current environment. When we look more at organ systems, we're looking at the pulmonary and circulatory systems. Did we get oxygen there? Did we remove carbon dioxide? Those are big, easy ways to kind of control that unchanging level, that steady meet supply and demand. When we look at a biological control system, we have to understand what's happening in our body. So we have to have three components. We have to be able to sense what's happening. We have to be able to process that. And then we have to be able to affect a change. So that sensor is going to see what has changed. Our control center is going to say, do I need more or less of something else to manage that? And the effector is going to be what puts the environment back to neutral, normal, that state of continued existence. So we have, two different kinds of ways to do that. Most of the time we operate through a negative feedback loop. We see something come up too high, we process that, so then we change it so that we can bring that back down, all right? So again, we just have to look at, do we have too little of something? Do we have too much of something? Like I said, negative feedback is going to be our most common. So what happens is the opposite of what we're seeing. So whatever initial disturbance happens, we'll try and counter that. So if we look at it, we might see that we're starting to increase our extracellular CO2. That triggers a receptor. It tells the respiratory control center, we need to increase breathing so that we can blow off the rest of the CO2 concentration and bring it back to neutral, normal. So that is that negative feedback loop. We had too much, we come back down. Positive feedback loop is going to increase our response to the original stimulus. So if we had more, we want even more. Again, not a lot of this exists in our body, but one of them is going to be childbirth. So what happens is we're going to stimulate receptors in the cervix. It tells your brain, release more oxytocin from the pituitary gland, and that helps promote more uterine contractions because we need more so that we can eventually, you know, discharge a human. So how do these all work? How do we put them together? Is it a little tiny trigger that can minutely manage something, or is it large? So we're going to call that degree. So the system with a large gain is more capable of maintaining homeostasis than something with a low gain. So if we look at the pulmonary and cardiovascular systems, they have large gains. Changing our breathing and jacking our heart rate, both will overcome something rather quickly versus looking at something chemically wise that takes a while to circulate and make changes. So our review, 9 times out of 10, 95, 97 times out of 100, we're going to exist through a negative feedback loop. We have too much, we've sensed it, our control center process it, and we affect a change which brings it back down. Now, the gain of that system, how much it can change and how quickly, really is going to depend on how much we need that system's help to maintain homeostasis. So let's look a little bit more at this homeostatic control. Temperature. So when we talk about body temperature, we've got thermal receptors. They start to indicate and send a message to our brain. When that happens, if our temperature is going up, we'll have a response by our skin blood vessels and sweat glands, all to regulate that temperature. Let's look at regulating blood glucose. That's going to be a function of the endocrine system. So we need hormone insulin. So what happens is, as we see elevated blood glucose signals, then the pancreas understands, processes this, and it releases insulin. Insulin causes the cells to uptake glucose so that we can maintain the activity that we're doing. So here's just another pictorial looking at body temperature and negative feedback. So if we know our set point should be 37 degrees Celsius, and we start to see that our temperature is going up, we're going to see that that stimulus tells our sensor, our control center, that, hey, our set point should be 37 degrees Celsius. So our blood vessels are going to dilate, our sweat glands are going to secrete, so we're going to bring it back to normal temperature. Let's go the same way, but now let's look at it as our temperature is low. We're going to see that stimulus tell our sensor that, hey, you know, we're dropping down below that 37 degrees Celsius, and you're actually going to see blood vessels constrict, the sweat glands become inactive, and that is going to bring us back to a normal body temperature. What happens if we fail? What happens when this doesn't go the way it's supposed to? We're going to see a disturbance in homeostasis. Let's take a diagnosis of type 1 diabetes. You know, we don't have beta cells in the pancreas functioning the way they should. So insulin's no longer being released into the blood. We become hyperglycemic. So the effector has failed because it hasn't controlled it. So as you can see, exercise is going to be a test of the system. You know, it's going to disrupt homeostasis in a variety of ways. We're going to see changes in pH, O2 levels, CO2, temperature of the cells. So if we're looking at submaximal exercise in a relatively cool environment, we should be able to control that. You know, our system should allow it. Where we start to get into failure will be intense exercise, prolonged exercise, anything in a hot humid environment. Often that will exceed the ability to maintain steady state. What happens? We're tired, we have to stop activity. You know, think about practice. You know, we're rolling into fall. you know, heat acclimation and just having 2-a-days versus one longer practice as kids come back and start sport activities. You know, that's something to truly consider, you know, what that environment looks like. Do they run the marathon in the Olympics at noon, like midday sun? No, they're up at daylight running that marathon. You have to look at what you can maintain before the system fails. So how do we get used to it? How do we adapt? How do we acclimate? Adaptation is going to be a change in our structure or function of the cell or organ system, all in an effort to improve our homeostasis. Acclimation is how do we adapt to the environmental stresses, like heat stress. You know, there are things that our body can do to make us improve and function there better. You know, and how does some of this work? The cells start to signal, they communicate between them using chemical messengers. So we can start to coordinate cellular activity. You know, we need all of those things to maintain that ability to continue. So again, I'm not going to read you everything on the take-home message, but recognize those things are there. How do we do it? There's a lot of different methods. Am I going to sit down and ask you to memorize? We get back to need to know, nice to know. These are going to be more nice to know. We can have signaling inside. So the chemical messenger inside the cell triggers a response. We can have it pass between two connected cells. We can act as a chemical messenger on that same cell. We can have something act on nearby cells. We can have hormones that are released into the blood, which just affects specific receptors to that hormone. There's a lot of different ways that cells can signal something's happening. So again, just another pictorial looking at this. Am I going to ask you and test you on these different ones? No. Recognize it's a complicated system with a lot of moving parts. You know, stress proteins. Cells that synthesize stress proteins, heat shock proteins, when homeostasis is disrupted. They are good. We look at these stress proteins and by definition of the name, we think they're bad. They're released in times of stress, but they're actually to repair damaged proteins within the cells. So, you know, stress, what does that mean? High temperature, low cell energy levels, abnormal pH, cell calcium changes, or protein damage by free radicals will all create these stress proteins so that our body can repair itself. So high intensity, prolonged exercise absolutely promote each of these stresses. So we know that protein synthesis improves our ability of cells to maintain homeostasis. So what happens? Exercise activates cell signaling pathways, activates transcriptional activator molecules. That transcription binds to a gene promoting in a region. DNA transcribes to messenger RNA. Messenger RNA leads to the nucleus and binds to the ribosome and is translated into a protein. So what do we have to know? Resistance and endurance exercise promote these different cell signaling pathways. They're good. We have to be in that position where we stress the system so the system understands how to repair itself and move on. You know, so much of our problem is if we end up in a position where we haven't been, our body doesn't quite know how to handle it. So how does this protein synthesis work? You know, during muscle contractions, we start to trigger this activation of the pathway. Starts to transcribe and change that DNA to messenger RNA. It's transported out and is translated into the protein, all geared at trying to protect and assist. So recognize cell signaling mechanisms are important. They can affect a lot of different tissues, whether that's inside the cell, a few cells, a bunch of cells, cells with a receptor. It doesn't matter. It matters that we have the ability to control and fix. So that is pretty much adaptation and how we get used to things. Again, most of this, a lot of this should not be unfamiliar, okay? It'll be something that you've encountered in some of those prior courses. Just want to review it and put it in terms of exercise. You know, the physiology that we do is all applied at this point, and that's what we're looking at trying to do. Chapter 3 is coming.